Good day, everyone. My name is Paula Grace Aquino, and today I will be presenting to you my thesis study entitled Molecular Docking Studies of the Bioactive Compounds of Centella Asiatica L on Different Neuroreceptors. To give you a brief background about this study, let's first talk about what Centella Asiatica is. Centella Asiatica, which is commonly known as Coca-Cola and in the Philippines known as Takip is getting more recognized for its adaptability and efficacy that many studies have proven. So from previous studies both in vivo and in vitro, they observed that Coca-Cola can enhance memory, reduce anxiety and depression through the modulation of the GABA receptors, and improves brain functions. So studying further the plant extract that they were able to determine the bioactive compounds responsible for these effects. So these are the asiatic acid, madecassic acid, asiaticoside, and madecassoside. However, no mechanisms have been established on how these compounds may affect neurological activities. Thus, this study would like to determine the possible interactions of the bioactive compounds on different neuroreceptors. Here, we're going to look into what neuroreceptors are. So neuroreceptors, which are activated by neurotransmitters, play an important role in the activities of the brain. So there are many classes of neuroreceptors, but this study will only be focusing mainly on GABA, dopamine, and serotonin receptors. So GABA A or GABA B receptor, they respond to the neurotransmitter GABA, which is the chief inhibitory neurotransmitter in the vertebrate central nervous system. So GABA plays an important role in memory, behavior, cognition, and the body's response to stress. So for the dopamine D2 receptor, so this study will only be focusing on the D2 receptor, where it functions mainly in locomotion, attention, sleep, memory, and learning. And it plays a prominent role in memory. So for the serotonin receptors, we will be having the 5' 1B and the 2B receptor. So they are also activated by a neurotransmitter serotonin. So serotonin receptors influence various neurological processes such as anxiety, cognition, learning, memory, and mood. Once again, the general objective of this study is to perform in silico studies on the possible binding and interaction of bioactive compounds of Centella asiatica with different neuroreceptors. So specifically, to determine the binding affinity and molecular interactions of selected bioactive compounds of Centella asiatica with different neuroreceptors. To identify potential ligands that may act as agonists or antagonists on given neuroreceptors, and to assess the drug likeness of the bioactive compounds through pharmacokinetics software tool. So the significance of the study is to give insights on the probable interactions of the bioactive compounds of Centella asiatica with the selected neuroreceptors that may have influenced neural activity, and to provide a study that can be used for further in vivo and in vitro studies in the future. So for the scope and limitations, the study is limited only to the docking analysis and will not be able to fully simulate in vivo conditions. It can only generate the binding affinity and conformations of ligands. It will not bind to any other site but the normal receptor sites. It is also limited only to molecular docking analysis and will not be able to simulate using molecular docking, using molecular dynamics rather. So here is an overview of the methodology. The first is the ligand structure preparations. Here, the 2D structures of the bioactive compounds of Centella asiatica and the natural ligands of the neuroreceptors will be downloaded from PubChem database in SDF format. So the natural ligands, binding affinity and interactions with the neuroreceptors will be compared to the bioactive compounds of Centella asiatica. Next is the protein structure preparation. Here, the 3D structures of the neuroreceptors will be downloaded from RCSB protein data bank, and afterwards, all these target proteins were first purified by removing the natural ligands, water molecules, and other heteroatoms using PyMol software and were saved as PDB format. So to identify the binding sites of the receptors for GABA A and GABA BR, the binding sites were determined from the structure downloaded from RCSB for the natural ligand GABA is bound in the structures and the binding sites of GABA and GABA receptors were located using primal software. And for the dopamine and 5-HT receptors, their binding sites were determined according to previous literatures. So for the molecular docking studies, it was conducted using Autodoc 4.2. Autogrid program supplied with Autodoc 4 was used for the preparation of grid maps, and the grid maps was adjusted according to the highlighted binding sites of the protein. All the default parameters of Autodoc 4 were followed. So the inhibition constant of the compounds was determined according to the theoretical calculation of Autodoc 4.2. The binding affinities were reported as kcal per mole. The binding affinities of the bioactive compounds of Centella asiatica were compared to the binding affinities of the natural ligands. So ligands with higher binding affinity than the natural ligand were considered as potential candidates. So the 3D protein ligand complex were viewed using Primal software, and the 2D interactions of the protein ligand complex was viewed and generated using the post-view tool from Protein Plus web server. Lastly is to determine the pharmacokinetics and drug likeness of the compounds. So Swiss ADME online web server was used to generate the pharmacokinetic properties and the drug likeness of the compounds. The boiled egg model of the molecules was predicted to determine if the selected ligands has the capability of gastrointestinal absorption and permeability of the blood-brain barrier. And Lipinski's rule of 5 was used for the basis of the drug likeness of the compounds. So for the results and discussions, here table 4 shows us that the binding scores generated from the molecular docking simulation along with their main residues. So the residues that have asterisks are the residues that are present in the original binding site and the redox protein ligand complex. So these are the binding affinity that will be compared from the binding affinity of the bioactive compounds in the neuroreceptors. Here is the 2D key interaction that was generated from the post-view tool in Protein Plus web server. So the redox natural ligands did not dock in the expected behavior as it was in the original complex that was retrieved from the PTB database. However, the redox GABA is still bound mostly to the active residues found in the original complex of the GABA A receptor and GABA B receptor. For the D2 receptor and 5-HT receptors, so the binding sites were found to interact with most of the active compounds based on previous literature. The binding affinities that were generated in the redox simulation were still used as the standard of the study. The hydrogen bonds are represented by broken lines, while the hydrophobic interactions are represented by green spline segments. So these interactions were used as the basis of comparing if the bioactive compounds of Centella asiatica have the same binding sites or if they dock near the binding sites of the selected neuroreceptors. Here is the binding affinities that were generated from the docking simulations. We can see here that madecasic acid has the highest binding affinity among all the bioactive compounds in GABA receptors, dopamine receptor, and 5-HT2B receptor, while asiatic acid was found to have the highest binding affinity among all the bioactive compounds in 5-HT1B receptor. The docked ligands were viewed in 3D and 2D using Primal and post-view in Protein Plus web server respectively. Here is the 2D interaction generated by post-view in Protein Plus web server. Here we have the GABA AR in complex with GABA and GABA AR in complex with madecasic acid. Comparing these interactions, we can see that madecasic acid were able to bind on one of the binding site of GABA AR, which is the residue THR202. For the GABA B and madecasic acid, we can see that madecasic acid was also found to bind near the binding site THR130 of GABA B receptor. While for the dopamine D2 receptor and madecasic acid did not bind with the binding site of the D2 receptor but still interacted with other amino acids within the vicinity of the binding site, which can be an allosteric site of the D2 receptor. For the 5-HT2B and madecasic acid, the madecasic acid was able to bind on one of the binding site of the 5-HT2B receptor, which is the residue THR140. And lastly, for 5-HT1B receptor, Asciatic acid was found to have the highest binding affinity, and here is the 2D interaction of asciatic acid in 5-HT1B receptor. So here we can see that asciatic acid was able to interact on one of the binding sites of 5-HT1B receptor, which is the residue PHE1330. Comparisons of these 2D clear interactions of the natural ligands and bioactive compounds of Centella asiatica both exhibited hydrogen bonding, van der Waals, and hydrophobic interactions to the functional groups found at the binding site of the neuroreceptors. So a stable complex between a receptor and ligand can be formed when it exhibits more high binding affinity and low inhibition constant, which indicates a high potency to be an inhibitor. So based on table 6, asciatic acid was found to have low inhibition constant, indicating that it showed high potency to inhibit the 5-HT1B receptor. On the other hand, medicasic acid may act as agonist. However, further research and study must be conducted to confirm this theory. So for the pharmacokinetics of the compounds, the figure shows the boiled egg model for the compounds of Shantella asiatica. So the boiled egg model predicted that asiatica acid and medicasic acid shows high GIF absorption in which both are also predicted as PGP plus as shown in table 7, whereas the other two compounds, medicasoside and asiaticoside, showed low GI absorption and all the compounds did not exhibit blood-brain barrier penetration. And lastly, for the drug likeness of the compounds, so table 8 shows us the molecular properties of the compounds. So based on this table, asciatic acid and medicasic acid were under the rules of Lipinski's rule of 5, where it should not violate 2 or more of the rules. So this rule is commonly used. Rule-based filter for drug likeness of a compound. So the following are the criteria for these rules. So number 1 is the molecular weight should be less than or equal to 500 Dalton. The log P should be less than or equal to 5. The number of the hydrogen bond donors should be less than or equal to 5. And the number of hydrogen bonds acceptors should be less than or equal to 10. So under the rule of 5, a compound or molecule is said to be an orally absorbed. It can be orally absorbed if it has no more than one violation of the above rules. So however, the asciaticoside and medicasoside have violated 3 rules, which cannot be considered orally active drugs. Other important properties for the drug likeness of a compound are its total polar surface area, where the total surface area should be less than 140 squared angstrom. So only the asciatic acid and medicasic acid had the above properties. Hence, only asciatic acid and medicasic acid possess a good pharmacokinetic profile and can be a potential lead for neuroreceptors modulation. So for the conclusion, the objectives were placed on the left side. So to conclude, the binding affinity of the 4 bioactive compounds, which are the asciatic acid, medicasic acid, asciaticoside, and medicasoside, were comparative to the binding affinity of natural ligands to the neuroreceptors. So both the natural ligands and bioactive compounds exhibit hydrogen bonding, van der Waals, and hydrogen interactions to the functional groups found at the binding site of the neuroreceptors. Here, the ligands that shows to have a potential to act as an agonist or antagonist on the neuroreceptors are the following. So here are the binding scores of the medicasic acid and asciatic acid on the neuroreceptors. So here, the binding affinities of the bioactive compounds of the Centella asiatica showed more negative binding scores than the natural ligands. Thus, the medicasic acid and asciatic acid can modulate the action of the neuroreceptors. And lastly, both medicasic acid and asciatic acid pass the drug likeness test, which is the Lipinski's rule of 5, and have high permeation for gastrointestinal absorption. So for the recommendation for further study, so based on the findings of the present study, it is recommended to study the activities of the bioactive compounds of Centella asiatica through in vivo studies. It can also be recommended to do a molecular dynamics simulation for the said compounds to further study its mechanism in the neuroreceptors. Thank you.